Let us learn theorems from chapter 10, Circles. Theorem 1 states that the tangent at any point of a circle is perpendicular to the radius through the point of contact. It means what I need to show in this, if a tangent is given, I need to show that OR is perpendicular to this xy or this tangent is perpendicular to OR. What is given? A tangent xy to the circle with center O. Tangent is given to us and OR is the radius of the circle. What I need to prove? I need to prove that OR is perpendicular to xy. Construction: take a point A on xy and join OA. Now you can see that this OA is intersecting the circle at point B. Now let us start with the proof, and before starting the proof I will repeat, for proving any of the theorem we need these main 4 steps: statement, then figure. With the after the statement we need to draw the figure, then what is given to us, what is to prove, and construction if any. Then we need to start with the proof. Now before starting the proof, let us first learn that if any circle is given with any center, suppose the circle is given with center O and this is the tangent, then the shortest distance from this center O to this tangent will be the perpendicular. Here, because you can see that these are also the distances, lengths from center to this tangent, but these are not perpendicular. The shortest one will be the perpendicular. You can see that these angles, you can see that these are not 90-degree angles, either from here or from here. If we will see, these are not 90-degree angle, but this is the 90-degree angle. So shortest of all will be the perpendicular. So here I need to prove that OR is perpendicular to xy. So for that I need to prove that OR is the shortest distance. I need to prove that OR is the shortest distance. So let us prove this. In this you can see from the figure or with the help of the construction that OA is greater than OB, right? The length of OA is greater than OB. It is clearly seen. Now OB and OR are equal because they are radii. So OA is greater than OR as well, as OB is equal to OR. Both are radius of the circle. Now as OA is greater than OR, now A we have taken any arbitrary point. So if we will be taking any other point on this line xy, definitely it will be greater than OR. So this implies OR is the shortest distance, OR is the shortest. So if it is the shortest, it means it is perpendicular to xy. So this implies OR is perpendicular to xy, hence proved. Now the next theorem from the same chapter, theorem 2, there are mainly only 2 theorems in this chapter whose proof can be asked in the exam. One was this that we have already discussed, and the second one is statement: the lengths of the tangent drawn from an external point to a circle are equal. So what is given to us? Tangents PA and PB to the circle with center O. We need to prove that the lengths, their lengths are equal. That only we need to prove. The lengths of tangent drawn from an external point P to a circle are equal. We need to prove that PA is equal to PB. Construction: we need to join OA, OB and OP. Now let us prove this. In triangle we are going to consider triangle OAP and triangle OBP, as these are the tangent and these are the radii. So these will be perpendicular using previous theorem. In the previous theorem we have proved that the tangent will be perpendicular to the radius. So these two are 90 degrees. So OAP is equal to OBP, each 90 degrees. Basically I need to prove that these two triangles are congruent. So the first step is, first thing which is equal is 90 degree, and the next is OP is equal to OP. This is the common side, and then OA is equal to OB, radii. both are radius of the circle. Now you can see that right angle, hypotenuse and side. This is the right angle, this is hypotenuse and this is side. OP is the hypotenuse. Hypotenuse is the opposite side to the perpendicular. So this implies triangle OAP is congruent to triangle OBP by RHS congruency. RHS congruency. Now if the two triangles are congruent, their corresponding parts will be equal. So PA is equal to PB by CPCT. CPCT stands for corresponding parts of congruent triangles are equal. So these two are corresponding part of these two congruent triangles, so they will be equal. Hence proved.